So if you go to Wikipedia and you look up entropy, or you look in the dictionary, you'll discover that there's something kind of shocking going on. So entropy originally was a concept from thermodynamics. And entropy is like charge, is a perfect analogy between entropy and charge. So when you take electrons and you pump them into a capacitor, you can store so many electrons. Q is equal to CV. So Q is equal to CV. And Q is the number of electrons times the charge of an electron is equal to C naught V. So the number of electrons is equal to, take the capacitance, 1 microfarad, and the voltage that it charges to, and divide it by the charge E. This is the charge of an electron, and that's how many electrons there will be in that capacitor. Now that's a very, very physical explanation. And S, the entropy, is the charge. It's equal to how much heat there is in water. So you take a cup of water, and it is at a temperature T, and has a volume V, and there's a heat capacity at constant pressure. There's also a heat capacity at constant volume. So if you seal this and you bring it up to temperature, then it's got a different capacitance than if you leave it open and you bring it up to that temperature, because PV over T, the water is going to expand. And so the amount of energy that you can store in that water depends whether it's a pressure cooker or whether it's open to the air. And there's two different numbers, and these numbers were all defined back in the mid-1800s, and they perfectly understood it, and they called it, Clausius, or one of those guys, called it entropy. So this is the entropy, and in information theory, John von Neumann suggested to Shannon that he call his measure entropy. And Shannon bought it. And he probably didn't know any thermodynamics. So the word entropy, I'm suspecting that I'm the only person alive who knows this, but I've researched it pretty carefully. The word entropy has two completely different meanings. One is the amount of heat in water at a given temperature per degree. So when you take water and you put it in the microwave and you heat it up, the temperature goes up, and it goes up by a predictable amount. The amount of energy that goes in there depends on how many watts the water absorbs, and whether it's an open or a sealed container. If you have an egg and you put it in the microwave, it explodes because it's a sealed container, and there's a lot of pressure that builds up. But if you take water and you put it in a sealed container, you get a pressure cooker. And anybody ever cooked with a pressure cooker? It cooks the vegetables about 5 times faster than if you'd put it in a pot. So, two different concepts, totally unrelated to each other, except John von Neumann, who is one of the world's geniuses, he gets it. He thinks, why don't you call it entropy? Because that's a measure of randomness, and information is a measure of randomness, so why not just call it entropy? And create one of the most chaotic confusions of chaos that ever existed, which is, what is entropy? I asked you what was entropy. Nobody knows. But entropy is just like charge. And the thermal impedance is given by the temperature divided by the entropy rate. And that's just like charging a capacitor with a current through a resistor. It goes up in its voltage. So voltage is like temperature, and entropy rate is like current. Let me get this right. Entropy rate is like current, I, which is Q dot, where Q is the charge. And the voltage over the current is an impedance. It's an electrical impedance. And the temperature over the entropy rate is a thermal if that word were any longer, I wouldn't write it. It's a thermodynamic impedance. Just like the voltage over the current is an electrical impedance, the temperature over the entropy rate, the rate of flow of heat, is a thermal impedance. And this capacitance, so this is 1 over Cp or LCV times times the volume, I guess. I have to think about that for a minute. Per degree. So the temperature over the entropy rate, Q is equal to CV over here. Q, where did I write that? I wrote it someplace. Q is equal to CV, and the entropy is equal to C sub P or else C sub V times T. Did I have that right? No. C sub P times the volume is equal to, I don't know. It's in my book, and I don't carry it around in my head very accurately. But Q is either the heat or the charge, and it's equal to C in microfarads times the voltage, and Q is the entropy, so we'll call it S, is the entropy, and it's equal to C sub P or C sub V times the temperature. And the temperature over S is 1 over C sub P or C sub V, and the units, you have to get the units right. So C sub P and C sub V are the amount per unit volume. So you take a glass of water, you put it in the microwave, you put the microwave on for 1 minute, and it's a 1 kilowatt microwave, and it boils, and you calculate the volume of water, and it went up from room temperature to 100 degrees in 37 seconds with 1 kilowatt of input. You have enough information. You can calculate. You know C sub P. You could calculate if you know how much energy is coming out of the microwave at 1 kilowatt, going into the water and being absorbed, then you can calculate everything just as easily as you can write down Ohm's law and calculate how many electrons there are. How many electrons are there if you got 1 volt, and this is 1 microfarad, and you know this 10 to the minus 18 is the charge of an electron, you can calculate how many electrons there are in that capacitor. That's amazing. And with heat, it's no different, except nobody documents it. Now, it is documented, but you have to go back 100 years to read about it. So I've put in some considerable time trying to figure all of this out, and I hope anybody have any questions about this? So it's a massive cover-up. They don't seem to want anybody to know what entropy is, because it's got 2 definitions. They have no relationship to each other, except for Johnny Neumann, who came up and told Shannon, why don't you call it entropy? Now let's talk about information. I'm done with that unless you have a question.
Yeah, super quickly. So entropy in thermodynamics is the amount of heat in water, and then in the other definition...
Or in any material.
Right, in any material. And then the other definition would be...
The amount of heat per degree.
Per degree, right. And then in the other definition...
Well, we're going to talk about it right now. Okay. So if you're confused, that's why. Now, let's talk about information theory. So first, information can only be measured by integers. Okay, so what is Shannon's definition? This is much more useful. Shannon's definition of information, he actually talks about integers, and he talks about specific cases. But he says information is 1 over the probability of, so information is a distribution. It's a probability distribution, and the distribution is in let's say you flip a coin 100 times, you're going to get 1, 1, 1, 0, 1, 1, 1, 1, 1, 0, 1, 1, 1. And you look at how many heads there are, how many tails there are, and then you count that, and the probability of getting a heads is 1 over, so you can write this in terms of P and Q, this probability. So if the probability is very, very small, then the information is really large. Because if you want to send, I have this morbid example that I used to use, and I thought I was going to be rid of this. But let's say your brother, your sister, or your father calls up, and they get you on the phone, and they said, your mother just died. You go, what? You're only going to get that message one time in your entire lifetime. And you're pretty much guaranteed to get it, unless you die of a car accident. Because you only have one mother, and she's only going to die once. And so the probability of it happening during your lifetime doesn't have anything to do with the probability of your life. You're going to outlive your mother. So it's a pretty rare event, and it only happens once. So there's a lot of information, and you feel it. That's why I use this. It really carries a strong message that if your father calls you up and says your mother died, or vice versa, that is a big deal. It's a lot of information in one short phone call. Now, I wish I could come up with a better example because it's so morbid, but I also need an example that carries a lot of information. So that's why I use it. Okay, so he says the information. So this might be the number of days that you went without the phone call, and then the sunrise on the 5,001th day, so the probability of the sun rising is 1 in 5,001. Now, and Shannon in his paper says, if you want to generalize these to the continuous distribution, you can't. I read that and I said, what? That makes no sense. Well, now, to me, it makes sense. But I had to think about it for a year or 2 or 5 years. The reason it doesn't make sense is because information is quantized in terms of integers. So you can't shift this whole scenario over to rational numbers because there's no information in rational numbers. You have to work with integers. And Shannon doesn't explain that. At least I haven't found it. So it's a probability distribution in the integers or in the odds ratios. And now once you have this piece of information, no pun intended, that information is 1 over the probability of something happen, 1 in 5,000 times. We've seen the sun rise 5,000 times, so the probability is bounded by 1 over 1,000, 5,001, and that number is completely ridiculous because we now know the sun is a thermonuclear reaction and it's going to keep on going for 4 billion more years, at least. Of course, by that time our planet will be all burned up because the sun will become a red dwarf. But 4 billion years, we're pretty much guaranteed we're not going to be alive in 4 billion years, nor will any of our relatives, and we better find a way to escape into space someplace and go find another planet that's habitable because this one won't be in 5 billion years. I don't know any more about it than you do. So what is information? This is the information density. It's a probability distribution. This is probability. And so the information is the expected value of the information density. And so this is the sum over k of p sub k log ln, log base 2, of the information of k. So it's minus the sum of p sub k log of log base 2 of p sub k. Because this thing is equal to 1 over p sub k, and this is log base 2, and because it's 1 over, it puts a minus sign out here. And that minus sign comes because I is the reciprocal of p sub k, so it's p log p sub k log p sub k, that's the expected value of this. That's information. This is the entropy. It's the expected value of the probability. And you can plot this, and it's very meaningful, and